All right, so I'm going to start lecturing. I'm hoping that everyone's turned in their exams by now. I hope everything went okay. Oops. I guess I didn't have my audio on, sorry. I'm hoping that everyone's turned in their exams by now, so I'm going to start lecturing. Can you hear and see me okay?
Yeah, I can see.
Okay, cool. All right. So what I want to do today is talk about applications of forces on charged particles in magnetic fields. And I want to talk about the force on the wire in a magnetic field. And on Monday in the lab, what I'll do is I'll use some of the time to talk about magnetic torque and the electric motor, because the electric motor depends on the magnetic torque. So I'll use some time on Monday in lab, and it's not a long discussion. And then really I'll be done with chapter 29. And so if you look on WebAssign, you'll see I've changed the dates on the next 3 homework assignments. So take a look at the assignments on WebAssign. Okay, take a look at the due dates. As you folks were taking the exam, I graded the capacitor worksheet. And one thing I noticed is for some folks, there's a problem in the book. There's an example problem in the book. In chapter 26 is example 7, which pretty much answers the last question on that worksheet. So if you had a hard time with the last question on the worksheet, most people did well anyway, but if you had a hard time with the last question on the worksheet, please take a look at example 26.7, okay? Okay, well, it seems like some folks were okay with the exam. That's good. So we'll see as I grade them how the exam went. Just a couple of announcements. You should try to collect the data this weekend for the DC Circuits lab. And the lab will be due on the 25th. I haven't changed the date on Canvas, I don't think, but I'll change it. The actual write-up will be due on the 25th, so you really need to collect the data for this lab this weekend, because the write-up is going to take time. And if you have questions, if you get stuck, then you can ask questions. But if you do the lab at the last minute, then you're in trouble. Okay? So you got to get started early. So it's on you if you don't get started early, okay? All right. For this discussion on the force on a wire in a magnetic field, there is a worksheet. It's not a difficult worksheet. It's kind of along the line of the capacitor worksheet, just to get you go through and do a simple calculation for a force on a wire in a non-uniform field. Okay, and I'll do an example today, and I'm just going to lecture until I finish the example. Okay, so if I go over and you need to leave, that's fine. It'll still be recorded. Okay. All right. So we talked about magnetic fields. I introduced to you the idea of the magnetic field. And I did a little bit differently because magnetic fields are kind of a different beast as compared to the electric field. So I introduced right away the fact that the field lines, since we already know something about field lines, they form closed loops. And as a result, there's no such thing as a magnetic charge. And we talked about the force on a charged particle in a magnetic field, and experimentally it can be shown that the force on a charged particle in a magnetic field is perpendicular to both the velocity vector and the magnetic field vector. No work is done by a magnetic field on a charged particle. And then the last thing I want to say is magnetic fields really are a manifestation of relativity. Now, we're not going to spend a lot we might say some things at the end of the semester when we do relativity, but they are evidence of relativity, okay? So last time we discussed at the end of the class, we discussed the force on a charged particle in a magnetic field. And just to review, in order for a charged particle to experience a force in a magnetic field, it must be moving. Not only must it be moving, it must have a component of its velocity perpendicular to the magnetic field. Otherwise, it will not experience a force. And this force is perpendicular to both the magnetic field vector and the velocity vector. So right away, that should make you think of a cross product. And so the magnetic force is related to the magnetic field and the velocity vector through a cross product. And of course, you can evaluate the cross product using a determinant. However, we introduced the right-hand rule so that we can use it for simple cases. So let me erase my board. And we said that magnetic force is Q V cross B. Okay, that's the magnetic force on a charged particle. And this works whether or not the magnetic field is uniform or not. And this force does no work on these charged particles. This force is perpendicular to both of these two. And so, if you put a charged particle in a magnetic field, two things can happen. It can either force the particle to move in a circle. Actually, it's three things. Sorry. It can force the particle to move in a spiral. Or it could just, there will be no force at all. And this means the particle maintains its velocity. So this occurs, the first one occurs when the magnetic field vector is perpendicular to the velocity vector only. This occurs when the velocity vector has a component of v parallel and perpendicular to the magnetic field. And in this case, the velocity vector is parallel to the magnetic field. Those are the three cases. And you can derive equations for the position as a function of time for these two cases. In the introductory course, we don't do this case. Okay, we usually do this case. And that one's circular motion is easy to deal with. In fact, we really focus on the conceptual motion and not really deriving the equation for motion. You did that in 205 anyway. Okay, and this just keeps, and in this case, the velocity just stays constant. Okay. Now, if there's also an electric field, if there's an electric and magnetic field involved, then the force on the particle, if you drew a free body diagram, would look like this. This is the force due to the electric field, less the force due to the magnetic field. And we call this the full Lorentz force. That's named after Lorentz. This is named after Lorentz, but this takes into account, includes also the electric field. And you can do some problems where you have electric and magnetic fields. A lot of times the electric and magnetic field are crossed, they're perpendicular to each other. Those problems are a little bit easier to do. If they're not perpendicular to each other, then the problem's hard to do. And if you try to derive an equation for the acceleration for the object in this general case, the problem is a little bit difficult. You're going to have to solve a differential equation. Yeah, in fact, you got to solve systems of differential equations, and a lot of times they're not easy. We don't do those in this class. Okay? All right. So let me march through. The videos don't play very well, so I'm going to skip these. So we also talked about using the equation for the Lorentz force to define the magnetic field. And so we define the magnetic field as the force divided by the magnitude of the charge divided by the magnitude of the velocity vector, and then usually we make theta equals 90. And so the magnetic field, the unit, the main unit, the SI unit, is the Tesla. Okay, the unit, the SI unit for the magnetic field is the Tesla. We also use the Gauss. 1 Tesla is 1,000 Gauss. The size of the Earth's magnetic field is around 0.5 to 0.7 Gauss, which is not that big. And really, you only see, I mean, if you wanted to see the effect of the Earth's magnetic field, you want to look at it, look at it in terms of what happens to an electron. If you had an oscilloscope, a real oscilloscope with a cathode ray tube in it, you can actually see the effect of the Earth's magnetic field when you turn on the oscilloscope and just reorient the oscilloscope. The little beam, the dot that you see in the oscilloscope would move around. Of course, the oscilloscope I used the other day in my demo is not a CRT one, it's an electronic one. But if we were in the lab, we'd be using a real CRT. And then you would, if you reoriented it, the CRT, you would see the beam get deflected because of the Earth's magnetic field. Okay. So let me just show you the right-hand rule again as a reminder. By the way, you will learn several right-hand rules in this unit. So instead of writing out the determinant to evaluate this, if these two are perpendicular to each other, it's very easy to use the right-hand rule. So let's say that we have a particle moving in that direction, and the magnetic field is into the board. Then what I do is I take my fingers, take my palm of my hand, okay, point my fingers in the direction of V, curl them into the board towards the magnetic field, and then my thumb points in the direction of the force. And remember what I said last week, that only works for a positively charged particle. If we're dealing with a negatively charged particle, then I have to flip this around. Okay, if it was an electron, then I would apply the right-hand rule, flip my hand around. Or the other possibility is to use your left hand. But I'm going to try to use any left-hand rules. We really only need a right-hand rule because there's going to be several of them we're going to learn. Okay, and that right-hand rule is a byproduct of the cross product. So I want to apply the right-hand rule in a demonstration. So we talked about some of the characteristics last week of magnetic fields. I want to demonstrate a charged particle in a magnetic field. So let me fix my camera. I really need a second camera to do some of my demos. Oops. And I'm going to point wrong way. Actually, I'm going to have to move my equipment. Hold on a second. Let me magnify. So I have something called a Crux tube. and I have a device that generates a high voltage. It's basically a Tesla coil. I'm going to turn the lights down a little bit so you can see. So this device over here is the power supply. This is the Crux Tube. Now, I'm going to turn on the Crux Tube. Do y'all see that green?
Yeah.
Okay, so that green is an indication of the direction of motion of the electrons. The electrons aren't green, okay? But there's a gas in there. When the electrons go through the gas, they excite the molecules and the atoms that are in the gas. When the atoms and molecules go from their excited state to the ground state, they give off light of that color. Okay? So we can see that the electrons are moving to the right. Let me turn this off real quick. The electrons are moving to the right. And I want to use the right-hand rule. Remember, these are electrons. So the green light is an indication, evidence that the electrons are moving to the right. Okay, so I'm going to try to use the right-hand rule here. The electrons are going this way. I'm going to take a magnet. I'm going to take the north pole of the magnet and point it towards you folks. So the magnetic field, so V is going to be this way. The magnetic field is that way. And if I use the right-hand rule, V cross B, and I got to put my hand this way because my fingers don't bend the other way, right? Your fingers don't bend the other way. And I curl them towards the magnetic field. My thumb points downward. So the right-hand rule says that the electrons, well, I got to be careful. They're electrons. The right-hand rule says a downward force, but these are electrons. So the force is upward. So if I bring the magnet, if I take this magnet and bring it near the Crux tube, I should see the electrons move upward. So let's try that. And I got to be careful around this thing because it's high voltage. Okay, so you all see you can all see that green beam, right? You might not be able to see me, but you can see the beam. So now I'm going to take the magnet and bring it near the beam. Is the beam deflecting upward?
Yeah.
Okay, in accordance with the laws of physics. Okay, so you can see now the effect of the magnetic field on electrons. And it's hard to really learn this topic without really seeing what happens. So I kind of want to show you that. Okay, so if I flip the magnet over, the beam should go downward, which it does. Right? I have the south pole going towards the beam, towards the perpendicular to the beam. The magnetic field points into the screen, and so the beam deflects downward. Okay, I did attach a little magnet. These little teeny magnets. You can't see me right now. Hold on a second. I did attach a really small magnet. Let me turn this off. I don't want to get electrocuted. I have a little teeny magnet I attached to the end of this magnet. It makes the magnetic field stronger, so it makes the effect stronger. Okay. Any questions on that? Okay. I do have I can't, and if we were in class, I actually had a device which actually forces the electrons to go in a circle. You can actually see the circular path, but the device is too big and too expensive. I didn't want to take a chance on destroying it. But we do have a device where I can actually force the particles to move in a circle, and you can see the circular motion. All right, let me change my... magnification here. Okay. All right, so one more thing. So we did talk about the motion of the charged particle in a magnetic field, and we said that if theta is 90, we're going to get pure circular motion, which means that the magnetic field is producing a centripetal force on the charged particle, and so we set QVB. Remember, if these two are perpendicular, the magnitude is just QVB. We said QVB equals mv squared over r. And then we can solve for r. And you get the r is the momentum over QB. And since it's going in a circle, if you remember, the tangential velocity depends on r times omega. We can actually determine the angular velocity of the charged particle in the magnetic field. And you'll see that the angular velocity of the charged particle in the magnetic field has a really simple equation, just QB over m. So as long as you keep b constant, omega is constant. The rate at which the angle changes is constant. V will not. Well, V will, of course, will change. If I mean, you can make V change by making the radius bigger, but omega is constant. And there's actually a thing I'm going to show you later on where we can actually make the radius of motion bigger while keeping omega constant. I want to show you a device later on. It's called a cyclotron. Questions? Okay, so I did an example last week. We did a conceptual question last week, so I'm not going to go over this one again. Some applications of this, well, one of the big ones is what we observe in space. If you, and these were discovered in 1958. They're called the Van Allen belts. The Van Allen belts are due to the Earth's magnetic field. These are charged particles that are trapped by the Earth's non-uniform magnetic field. In that figure, the purple and the blue are two of the main regions of the Van Allen belts. The closest, if you look at the inner belt, and the inner belt, the belts actually span the distance. So generally the closest distance to the inner belt is about 600 miles above the Earth to about maybe several thousand miles above the Earth. And then the outer Van Allen belt, the innermost portion is about 8,100 miles away. The inner Van Allen belt is mainly comprised of protons, and the outer Van Allen belts are comprised of electrons that are trapped by the Earth's magnetic field. Why is this important? If you send satellites in those directions, communications will be affected. And the reason why is because these charged particles are being accelerated by the Earth's magnetic field. Accelerated charged particles produce radiation. And these are pretty energetic particles. So if you were there in a spacecraft and you didn't have any protection, that radiation produced by the accelerated particles would be lethal. The Earth's magnetic field keeps those particles from entering our atmosphere. Although they can enter at the North Pole. Why can they enter at the North Pole?
I have no idea.
Well, because the magnetic field would be parallel to the velocity vector. And there's no force. Now, these are believed to originate from the solar wind. Any planet that has a magnetic field will have belts like this. Any planet, okay? And that magnetic field protects us from being irradiated by those particles. Now, when those particles get pretty close, and sometimes in the north they get pretty close, you can see the effect of those particles getting pretty close. It's the Aurora Borealis. You see that color there? The same color as in my tube that I showed you. Okay. Charged particle going through an atmosphere. So that's what you saw in my tube. So you see this in the north and in the south. The Aurora Borealis and the Aurora Australis. And sometimes they do get pretty low. They can get down to about 200 miles above the Earth's surface. You actually don't want them to get too close to us. And the reason why it happens at the north is because of the direction of the magnetic field at the north. So let me tell you about an application of these ideas in electric and magnetic fields. You'll see this in a lot of books, and they don't really give it the name, they just call it a velocity selector. Imagine I have two parallel plates, like you see in the figure. And I have charged particle coming in from the left and moving towards the right. And I only want particles of a certain velocity to get through. So I can use a magnetic field to let velocities, particles of certain velocity get through. So let me draw a picture on the board. So let me switch views here. So let me draw the parallel plates. And what you saw in the picture was the parallel plates and a magnetic field pointing into the board. This is for people who are working in, with accelerators in chemistry and physics. So let's say we have two plates. I'll let the top one be positive, the bottom one be negative. So the electric field points downward. And some particle going that way, and let's make it a positively charged particle. For example, an ion, a positively charged ion, maybe a molecule like H3 plus or H2 plus, something. It's just some positively charged molecule, okay? You can think of your favorite positively charged molecule, those of you who are in chemistry, and it's going this way. Now, if the particle is going from left to right, what's this electric field going to do? The electric field is going to bend it downward, right? So there's going to be a force due to the electric field that's downward. Because that's a positively charged particle. I only want particles of a certain velocity to go through here undeflected. So what I do is I introduce a magnetic field. I introduce a magnetic field into the board. So what does that do? Well, if I have particles going this way, and I have a magnetic field into the board, and if I do V cross B, again, put my fingers in the direction of V, curl them towards B. And by the way, if you don't like that, you can always set up a determinant. But the determinant is easy, right, for this case, right? How do I don't know if you remember how to set up the determinant. So you put the velocity vector here, and you have Q out here. You put the velocity vector here, so that's in the x direction. And then you put the magnetic field, and then you evaluate the determinant. You'll see that the force is going to be upward. So if you want to do it that way, go ahead, but the right hand rule a little bit faster. Okay, whatever makes you happy, I guess. And you can use one to check the other anyway. So the magnetic force will be upward. So what does that mean? So let me use the full Lorentz force. I know that the force is going to be up or down based on how I set this. So I'm not going to write this in terms of IJ notation. I know the force is going to be upward or downward. So I know that this is going to be downward, and this will be upward. And I want to set this equal to 0 so this thing goes straight through. Well, Q's cancel, and I get E is VB, and I get E over B is V. So that ratio gives me the velocity vector. So I set B up so that this force is 0, so I can get particles of a particular velocity get through. Now, you might ask, well, how do you keep the particles from getting through? I mean, if you have a big gap here, you're going to get a lot of different particles that get through, even the ones that get deflected slightly. Well, what you do is you put a little slit here, or a little hole with a small opening, and that narrows down the velocities that can get through. So you put a slot here in the center, or a hole in the center, halfway between the plates, so that only particles of that V will get through. If this B is not correct, nothing gets through. If this B is correct, then a bunch of particles get through. Does that make sense? And that's called a Wien filter. And it's used by chemists and physicists who actually use accelerators. I've used them in the past, and you'll see people in chemistry who will use them to select particles of a certain velocity. Because you see some chemists, they do mass spectroscopy, and they'll use a Wien filter. Questions on this? Okay. So another application, and this was done by Thomson. This is actually another application of the Wien filter. He was able to measure the charge to mass ratio of the electron. So let me blow this picture up so you can see it better. So Thomson used a device like this around 1905 to measure the charge to mass ratio of the electron. He was able to produce the electron with this, basically this first part is the electron gun. The beam was sent through, and there's a set of parallel plates that you saw it like in the previous slide. to think about the direction of the magnetic field in this figure. So one of the things he did to determine the velocity of the particles, he turned on the magnetic field so that the particles go through undeflected. Since he knew the electric field on the plates and he knew the magnetic field, he would get a direct measurement of the velocity of the particles that hit the screen. So the front screen, so you might be asking, how in the world is this guy from 1905 going to be able to detect these invisible particles? Well, what he did is he put phosphorescent screen here, just like on an oscilloscope. And so when the electrons hit the phosphorescent screen, it glowed. And so he adjusted the magnetic field until he saw no deflection of the beam. Then he can calculate the velocity vector. So once he knew the velocity vector, he turned off the magnetic field and then measured how far the particles deflected vertically on the screen. And if you know the geometry, if you knew the length and the separation between the plates, and you know the distance from the plates to the detector, you can calculate the charge to mass ratio. He was able to get 1.76 times 10 to the 11th coulombs per kilogram. And then a few years later, Millikan actually measured the charge of the electron. So the question is, would you be able to, on an exam, derive this expression? So on the next slide, I have the answer. You don't have, ignore the last sentence there, okay? You don't have to turn this in. But good practice for you, can you derive this equation? We do a lab when we're on ground where we derive this equation. But you guys don't have that opportunity. So for practice for yourself, because this involves methods from Unit 1 and Unit 3, you should try to derive that equation. And if you get stuck, just ask me. Let's say we have a charged particle that comes out of an accelerator. We send it from the accelerator into a magnetic field. So first of all, let's consider the velocity of the particle when it comes out of the accelerator. So we're reviewing Unit 1. And I'm just going to draw the accelerator as a box, okay? So here's our accelerator. And in the accelerator, the charged particles goes through a potential difference. So that Q delta V plus 1/2 m V final squared minus initial squared equals 0. Of course, V initial is 0. So we can find the velocity from conservation of energy and I'm writing this thing in parentheses under the square root as a positive number, okay? Because this depends on whether or not we have a positive or negative charge. So I made everything in here purposely positive. And so the velocity of the particle is just given by this expression. Now let's assume now we write our V's and our Q's, and my notes have not a delta V, but a V. Let's write this, assume they're positive values. Okay. Now this thing goes into a magnetic field. That is perpendicular to the velocity vector. Then we'll have Q V B is equal to m v squared over r. But this v is this guy because the particles originated from the accelerator. The particles got their velocity from being accelerated through a delta v. And that's important because, you know, depending on the particle that comes out of here, the velocities are going to be different. If you change the mass, you change the velocity. Pay attention to this because you have a homework problem in this unit where you have to consider that. Okay, there's a problem with particles coming out of an accelerator. And you have to separate two different isotopes. And you're going to have to use this idea to solve the problem. So if QVB equals mv squared over r, and we can solve for r here, right? R is going to be what? Get rid of one of the v's. Is going to be mv over qb. And the v is this guy. Running out of space. You can also solve for m. And you get m. If you rearrange this and solve for m, you'll get q r squared over 2 delta v. And again, I'm going to keep these numbers positive, b squared. If you take this and solve for m, you get that. And so I can, for a particular b, the particles will have a particular radius of curvature for a particular m. So this really forms the foundation of a mass spectroscopy, of doing mass spectroscopy. So I can have, let's say, a particle come into a magnetic field. If I know the radius of curvature, then I can figure out the mass. Typically what I do is I put a detector here. Of course, this distance is 2r. All right, this is twice the radius. Okay, so if I know the radius of the circle and I know the magnetic field, I can get m. Those particles that don't have the right mass, they won't hit the detector. Of course, I can make the opening small enough so I can just pick particles of a certain mass. And again, just be aware, there's a problem in your homework that's related to this. So this is called the Bainbridge version of the mass spectrometer. The first person to devise the mass spectrometer, his name was Aston. And this is a version that was designed by Bainbridge. Let me expand on this figure. So you have particles coming out of a source. Particles of a certain velocity are selected with a velocity selector. So let me say something. S1 is just a set of slits to narrow the beam because accelerator, when it produces a beam, stuff gets sprayed out everywhere. And so you only, your job is to collimate the beam as much as possible. Make it look like a beam instead of something that's spreading out everywhere. So there's actually a lot of stuff that goes on in the sources, focusing elements, etc. Just like an optical lens, except it's electrostatic lens. They go through a set of slits, and then this device is the Wien filter that selects particles of a certain velocity. And there's another set of slits here, again, to limit what gets through. And this is the magnet. In this particular case, the magnetic field points out of the board or out of the screen. And there's a detector here. Those particles with the right mass momentum per charge ratio reach this detector. And the other ones missed the detector. And if you've had chemistry, you've probably discussed the spectrometer. Because you also have, in chemistry, you probably learn more sophisticated techniques of determining mass. There's NMR and all kind of fun stuff. Questions on this? Okay. Another application is the cyclotron, which was developed by Lorentz and Livingston at Berkeley. And it's used to produce high energy particles for nuclear reactions at the time, but now they're used in hospitals to produce various isotopes for doing PET scans. And these isotopes are very short-lived because what you do is you inject them to the person's body so you can do the scan. These are like F18 and O17. These are isotopes that have a short lifetime. And this is what a cyclotron is like. You're forcing the particles to go in a circle, but you split the circle into two Ds. Remember what I said earlier, as long as the magnetic field is constant, the frequency or the angular velocity as they go around in a circle doesn't change. So what can I do for this system to make them go faster? First of all, the particles are generated at the center of the cyclotron. The two Ds are at different potential. So you have one D like this, and another D like this. And I've exaggerated the separation, okay? And let's say the particle is going this way. These two are at there's a potential difference between these two. And what you do is set up a radio frequency, and you actually don't keep that constant. These actually swap as these guys go around. These swap signs as you go around. So your electric field ends up being something like this. So maybe this is positive when it's over here, and then when it crosses again, you have this voltage, it's negative. And so it alternates. And so what you do is you use radio frequency to generate the alternating fields. And again, since B is constant, the frequency at which it makes a circular path doesn't change. So all you got to do is alternate this voltage or electric field at twice the frequency. And so each time it goes around, each time it hits the gap, it gets accelerated and it goes faster and faster and faster. Nowadays, the main ones are in hospitals. So there's a picture of a commercial one that's used in a hospital. Typically, the bigger hospitals have them. Okay, so the last topic I want to talk about today is the force on a current carrying wire in a magnetic field. Suppose I have a wire in a magnetic field. I want to consider the force on a wire. In fact, is it a significant thing, a force on a wire in a magnetic field? Is this something that I have to really think about? Turns out the answer is yes. And I'm going to demonstrate that to you. Okay? In order for me to figure out the force on the wire in the magnetic field, I have to figure out how much charge is in that wire of length L. All right, I need to figure out how much charge is in the wire of length L. And I'm going to use the same arguments as I did for really talking about current. I know that the force on one charge is Q V cross B. But in a wire, let's say I have n charges per unit volume going through a wire cross-sectional area A and length L. Number of charges per unit volume times the volume gives me the amount of charge in the wire of length L. Of course, let me move this to the other side. If you remember, N times Q times V sub D, the drift velocity, is the current density. So I can write this as J cross B times A times L. J cross B times the volume. This is the force per unit volume times the volume, but I don't want to write it that way. So if I want to, if I'm really looking at something that varies over the volume of the wire, then I can say over a small section of the wire, carrying current in some small volume, then the force can be written by this expression. And if this always varies, I can make this a D and that a D. But we're not going to do those problems here. We're going to keep it simple. We're going to say that everything's constant inside the wire. So let me write it this way. Since the velocity vector is in the same direction as L, I'm going to write it this way. What's J times A? That's just the current. And so the force on a wire in the magnetic field, and this is this is the force on the wire in the magnetic field, just I L cross B. L is the vector pointing in the direction of the current. Okay. I is a vector pointing in the direction of the current with magnitude equal to the length of the wire. Now that's assuming I have a straight wire. And this expression does assume that the magnetic field and the current density are uniform. So I'd like to demonstrate to you the effect of a force on a wire in a magnetic field. I just have to move some equipment. Now, my magnetic field will not be uniform. So just give me a second. I have to move some equipment so I can do my demo. So I'm going to do a demo with a fairly high current. In fact, high enough where I'm probably going to blow the fuse on my power supply. Okay. Again, I'm going to have to move my camera here in just a second. Okay. So, hold on a second. I got to plug my power supply somewhere else. So I have, can you guys see the big magnet? Can you all see the big magnet?
Yeah.
Okay. So, and you can see the power supply, right? Maybe, let me blow this up a little bit more. Okay. So here's the wire. I'm going to have a wire in the magnetic field. And I'm going to run a current through it. Ready? Do you see that? I'll do it one more time because it happens quickly. I can't have the power supply on very long because it's going to trip the circuit breaker because I basically have a direct short. But I need a sufficient current to be able to do this demo. So here we go. We'll do it one more time. Y'all see that?
Like jumped.
Yeah, it jumped, right? Because once I ran the current in the wire, which was in the magnetic field, obviously I had to have the current going in the right direction because if I flipped the current, it wanted to go down. Okay? I just love this thing because it happens very quickly. We'll do it one more time. Here we go. Okay, so the wire jumps out of the magnet. So that illustrates the force on the current carrying wire in a magnetic field. All right, let me fix my camera. Okay, I think we have everything back. What if I changes? What if the magnetic field direction, what if the current direction changes? What if I have a wire, that green wire that's bent? Then what? Then what I have to do is consider the force on a DS part of the wire. I have to write the force on a small element of the wire DS. So I got to say DF is IDS cross B. And then I have to sum over all the DS's. Well, what that means is I have to integrate over all the DS's. Of course, if I is constant and B is constant, then I basically have the integral of I cross B times ds. And what's ds? It's just a vector that points from A to B. So this clearly illustrates what L is. L is just a vector that goes from A to B. So F is still IL cross B, and this really clearly shows that L is the magnitude of the vector that points from A to B. Okay, that's our L. What if the current carrying wire forms a closed loop? What's our integral of ds then? If I have a closed loop, what's my integral end up being?
Would it be 0?
It's 0. Yeah, and again, what am I assuming? I'm assuming that B is uniform and I is uniform. Okay. Yeah, our total displacement is 0 because I can pull the B out of the integral. But if B is not uniform, it's got to be inside the integral. And I can't necessarily say that integral will be 0. So what I want to do is, I want to finish the day with this example. And I want to do it 2 ways. I want to do it the hard way, and I want to do it the easy way. It's always good to see the problem done more than one way. So I'm going to do it the hard way. And so let me draw a picture of this one. And while you're looking at it, I'll draw the picture and then I'll switch views. Just give me a moment. I have to erase the board and then draw it, and then I'll let you see the board. Okay, so, and you can read the problem. So this wire has current of 1 amp. And it's semicircular. And the current is counterclockwise. And I'm going to have to draw a radius vector. I'm just a radius. And let me switch views now. So here's my picture. So I'm going to denote, this is X, this is Y, B is in that direction. So B is, oh, it's in the wrong way, sorry. B is this way. Which is also the Z direction. 1.8 K hat Tesla. R is 0.25, I is 5 amps. And we know that F is equal to I L cross B. This assumes, everything is constant. I want to do it the hard way first, saying just thinking about the fact that the angle between the current, the L, not the L, but the angle between the direction of current and the magnetic field is that important? Actually, the angle between the current and the magnetic field is always the same. but the current changes direction. What I want to do is, I want to write a df. I want to write an expression for the force acting on a little section of this. Remember, the field's uniform. Okay. I want to write what this expression is for a small element of wire. And I'm going to put that in here. Question is, what is ds? Well, what's the magnitude? What's this distance going to be? If this angle, if this thing is small, this angle is d theta, and this radius is r, what's the magnitude of this vector?
RD theta.
RD theta. This vector points tangent to the circle. So this vector points that way. And if this is some arbitrary angle, got too many markers in my hand. If this is some arbitrary angle theta, I'm going to draw a coordinate system right here. What's this angle? What's that angle? If this is theta, isn't this theta?
So just 90 minus theta?
90 minus theta. So isn't the x component and the y component right? This is cosine of 90 minus theta, right? The x component is cosine of 90 minus theta, which is sine of theta. The y component is sine of 90 minus theta, which is cosine theta. So then I put this up here. And I'm going to integrate this thing from here to here. I'm going to integrate from 0 to 180 degrees. Okay. By the way, what's I cross K? How we can do that? What's I cross K? Isn't that the minus J direction?
Yeah.
Okay. So I cross K is in the minus J direction. So let me do it this way. I'm not going to write units because I'm going to run out of space. I have a minus sign there too, so that cancels the minus signs. And then what's J cross K? If I take J and cross them to K, it points that way, so it's in the I hat direction. We okay so far?
Yeah.
Okay. So I just want to check my math here. Let me double check my math. So I'm going to integrate this to find F. By the way, the current is what again? What is the current? 5 amps?
5.
What's 5 times 1.8?
9?
9. 9 divided by 4? Because R is a quarter. Is that 2 1/4?
Yeah.
Okay. What's the integral of cosine?
A positive sign.
Sine. And then you're evaluating it from 0 to pi. What's sine of 0?
0.
And sine of pi?
Also 0.
Okay. That one's gone. So now, what's the integral of this guy? Minus the cosine, right? So this is going to give you, this integral is going to give you 2, right? What's 2 times 2 1/4?
4.5.
So we're done. If the field was not uniform, this is how I would do it. If the field was not uniform, I'd have to put an expression for B, something with variables in it, and do the integration. That's why I did it this way. But what's the other way to do it? What's the easy way to do it? Remember, B is uniform. I mean, going back a few slides, when I wrote this down, L is the vector that goes from the beginning to the end, basically, right? L is the direction of the current. The current starts here. The current starts here and ends here.
So it's basically independent of path?
I'm sorry, it's independent of what?
Of the path of the...
Yeah, right. That's what I showed you before with when I set this up, right? When I set up the integral before, I showed that it was independent of the path.
All right.
Right. So it's basically the shortest distance between the beginning and the end points. And so L, really, I can write L as minus 2R I hat. It's a lot less work, isn't it? Okay, let's do this again. 2 times, where was I at? 2 times 1/4 is 1/2. 1/2 times 5 is 2.5. Two and a half times 1.8 is 4.5. And what's I cross K? Didn't we do that before? Isn't I cross K minus J? Same answer. But again, remember, I can only do this because B is constant. Don't forget that. I can only do this, write this, because B is constant. Remember what I did in my derivation. Okay. Are we okay with that?
Yeah.
Okay.
Yeah, it's-
So I'm going to stop here. I'm going to kind of way over. Okay. So you folks have a good weekend.
You too.
All right.